Today we're going to talk about how to draw a slope field and then how to use that slope field to sketch a rough idea of what the solution to a differential equation looks like. So the first thing we have to think about when we're sketching a slope field is the fact that the derivative of a function tells us the slope of its tangent line at any given point, or the slope of the function at that point. So if I were to think about some function y equals f of x, and I were to say that its derivative, dy dx, was equal to cosine x, that would tell us that cosine x indicates the slopes of f of x at any given x value. So what we're going to do is we're just going to evaluate dy dx at a bunch of different values of x and see what those slopes are. So we're going to start with x equals 0. If x is 0, dy dx is the cosine of 0, which is 1. And so what we'll do is we'll go over to our coordinate axis here, where I've drawn a bunch of points. And on the AP test, oftentimes with the slope field questions, they're just going to give you a bunch of dots on a graph and say, sketch the slope field at the indicated points. It will never be quite this many. It's usually somewhere in the 8 to 15 point range. Here we got way more than that. But that's okay. At x equals 0, we know that the slope of f of x is cosine of 0 or 1. So everywhere where x is 0 along the y-axis, we're going to just draw a bunch of little lines that have a slope that is approximately 1. And we know what a slope of 1 looks like, right? Up 1 over 1. So our slopes are just going to look like that. And we're going to do this then at a bunch of other values of x. So I'm going to say that this next column of points going to the right here is at x equals pi over 2. We'll call the next one pi, 3 pi over 2, and 2 pi. And going back in the negative direction, we'll use the same values. So if x is equal to pi over 2, then dy dx is the cosine of pi over 2, or just 0. Well, a slope of 0 just looks like a flat horizontal line. So we'll just draw a bunch of little lines here at all these points that are horizontal. And we're going to do the same thing going across. At x equals pi, dy dx is going to equal the cosine of pi, which is -1. And a slope of -1 looks just like this. And as we move over to 3 pi over 2, we're going to get dy dx is equal to 0 again. So we'll draw a bunch of little horizontal lines, indicating that at 3 pi over 2, the slope of f of x should be 0, it should be horizontal. And then at 2 pi, we're all the way back where we started, actually, right? Because the period of cosine is 2 pi. At 2 pi, dy dx is back to equal 1. So at 2 pi, they'll all be just a slope of 1. And now going backwards, I'm not going to write all of them down. We'll write the first one down here. At negative pi over 2, dy dx is going to equal 0, because the cosine of negative pi over 2 is 0. So these ones will all be zeros. And going back one more, at x equals pi, they're all going to be -1. And we'll note that as we're doing this, of course, in each column, they're exactly the same, because the y-coordinate doesn't affect the slope here, only the x-coordinate does, because we're only looking at cosine of x. Later on down the road, we're going to look at some differential equations that have both x and y, and we'll have to do some different things in these columns. We won't be able to just do the same thing in each vertical column. Moving back one more to -3 pi over 2, we're back to 0. And then at -2 pi over, -2 pi, the cosine of -2 pi is just 1. And so this is our slope field. And it's a general representation of what y equals f of x, or the solution to dy dx equals cosine x, looks like. In fact, it's a representation of all of the different solutions that we could get. Because remember, there's an infinite number of solutions to a differential equation, because we could add any constant to it. So let's kind of see how this works now by sketching a solution curve. So let's sketch f of x. If f of x were to go through the point 0, 0. So we're going to make sure that our solution curve goes through the point 0, 0. And we can see that at that point, our slope should be 1, right at that point. But as we move towards the right, as we go towards the right to this next column, our slopes should be decreasing from 1 to 0 on that interval. So I need to kind of start at 1 and move to 0. And right there, I should be now at a slope of 0. And as I then transition down to x equals pi, we're going to go from a slope of 0 to a slope of -1. It's going to look like that. And it's going to continue -1 until I get narrowed out to a slope of 0 and back up to a slope. That last one didn't look so good, but back up to a slope of 1. And in the other direction, we'll flatten out to a slope of 0, increase to a slope of 1, then back to 0, and then back to 1. And this is the solution to the differential equation dy dx. It goes through the point 0, 0. And what does it look like? Well, it looks like the integral of cosine. It looks just like a sine curve, right? A sine curve that has at x equals 0, it's right here in the middle of the line you oscillate around, starting to go up. And we could, of course, pick any point along here. Let's say we wanted to choose a different point. Let's say I asked you to use the point pi, comma, whatever this is. Let's call it pi, comma 2. And we'd see the same thing would happen. We'd be at -1, and we'd flatten out to 0, and then go back up to 1. And here we'd go backwards to 0, and then down to 1. And then we'd come back here to a 0, back up to the -1, flatten out as a 0, and come back down to 1. And it still looks just like a sine curve, just shifted up a couple of units, right? And so no matter what point we choose, it's going to end up looking like the solution to dy dx equals cosine x. It's going to look like sine x plus any constant. And so that's the basic idea behind what a slope field does. So this particular one, we knew what the solution was, right? We know that the solution to dy dx equals cosine x is f of x equals sine x plus any constant. But we're going to now deal with some more differential equations that we don't actually have means to solve in Calc 1 yet, or some of them we won't ever learn how to solve. So let's take a look at one of those. We're going to construct the slope field for the differential equation dy dx equals root x squared minus x plus 1. Got the equal sign in there, so we'll throw that in there. Dy dx equals root x squared minus x plus 1. And let's just call each of these here, these increments, we'll call this 0. We'll call this 1, 2, and 3, and -1, -2, and -3. It doesn't really matter what the y coordinates are here, because if we look at our differential equation, once again, it only involves x values. So in each vertical column, again, the slopes are all going to be the same, right? When I plug in 0, I say that x equals 0. dy dx is going to equal the square root of 0 minus 0 plus 1, which is 1. Right? It doesn't matter what the y coordinate is because there's no y in our differential equation. So everywhere along the y-axis, where x is 0, we'll have slopes of 1. And so what we'll want to do is just plug in 1, 2, 3, -1, -2, and -3 into this, and generally see what it looks like. So x equals 1. dy dx is now equal to 1 squared, which is 1, minus 1 gives you 0, plus the 1, square root of 1, just 1. So again, we're going to be at a slope of 1, which might be a little bit confusing. It's going to stay at 1 this whole time between 0 and 1, or does it kind of fluctuate in between there? And without testing a point between 0 and 1, we can't really tell. But we can have a general idea. Let's say we plugged in a half for that. Plug in a half, you get half squared is a 4. Minus half, -4, and add 1, make 3/4. And the square root of 3/4 is somewhere between 0 and 1, or less than 1. So we know that in between there it's going to be 1, and it's going to kind of flatten out a little, and then go back up to 1. But that's not generally something you're going to need to do with any of the slope fields that you'll have to do on the AP test. And then let's look at x equals 2. So if x equals 2, dy dx is going to equal the square root of, well, 2 squared is 4, minus 2 is 2, plus 1. So we're looking at the square root of 3. Of course, we don't need like a complete exact value for that, but I mean, we know that the square root of 3 is going to be between 1 and 2. It's like 1.7 something, something, something. So we need a slope that's a little steeper than 1, but not too steep. So we just want to be getting a little steeper in this column. And then we'll move out and we'll do one more over here. We'll take a look at x equals 3. And that'll give us dy dx equals the square root of 7. 3 squared minus 3 plus 1 is 7. And square root of 7, again, we should know that that's going to be between 2 and 3. And because the square root of 4 is 2 and the square root of 9 is 3, and 7 between those, it's going to be between 2 and 3. So we just need to be, again, a little steeper than we were in the previous column. And your slopes don't need to be completely 100% exact. Like you don't need to get a ruler out to measure them on the AP test. As long as you're in the general range of like pretty close to what it should look like, you're going to be in. Let's take a look at x equals -1. X is -1. Dy dx is going to be -1 squared is 1, and then minus -1 is 2, and then another one is 3, so square root of 3. So this is going to get just a bit steeper again. A little steeper than 1, but less than 2. And we'll move out to -2. And if we plug that in, that looks like that's going to be a square root of 7. So a little bit steeper again. And again, they don't need to be perfect. As long as they look a little steeper than the previous column, you're going to be okay. And the last one, x equals -3, dy dx is going to be, looks like, what is that? That's 9 plus 3 is 12, plus 1 is 13. So even a little bit more steep. Once they get so steep, it's kind of hard to get up to look good, but that's good enough. And again, we have a general idea of what the solution to this differential equation that we don't actually know how to solve would be. And if we pick a point, let's say the point 0, -1 here to draw the solution curve through, we should start at 1. And when we get back over here, we start at the slope of 1. And when we get over to 1, we should be at a slope of 1 still. And we said in between, it kind of flattens a little. So let's just kind of flatten it out. That wasn't very good. But we'll kind of have that be 1, flatten, and then back to 1. It's not much of a little flattening there, but good enough. And then it's going to just slowly get a little steeper as we move out. And same as we go this direction. It's just going to keep getting steeper as we go down and to the left. Every time we move to the left, it gets a little steeper. And in order to get full points on drawing a solution curve for a slope field on the AP test, you got to make sure of a couple things. One, that you go through the point that was indicated. So if I say go through 0, -1, your solution curve better go through 0, -1. It also needs to extend to the ends of the slope field. But you don't need to go beyond it. You don't want to go beyond it. You don't even need to draw arrows at the end. Right? Because we're only guaranteed that this is what it looks like right here on this interval that we're looking. So this would be a solution curve that would get you full points on the AP test. And of course, we could pick some other point. Let's say we chose -2, 0. We're going to be real steep real quick. And then we're going to flatten out some and kind of look like that. And as we went further to the right, if we had more space up there, we would deepen right back up. That's what this one looks like. So our next slope field that we're going to take a look at here is clearly a little bit different. Immediately, if you look at that differential equation, you can see that it's dy dx equals x minus y, which means we're no longer just looking at x values, we're looking at y values as well, which means that I can't just work with a single column at a time. I've got to come up with a different technique. And what we'll want to do here is just pick some values that we would like our slope to be, some simple, easy values. Like let's start with, we would like dy dx to equal 0. And so we're going to use this method where we just pick some easy values to start and see what happens. Anytime we have both x and y, and we are either adding or subtracting the two terms. So if they're multiplied or divided, we don't want to use this technique. We're going to use some other methods. But for adding or subtracting the two variables, we're just going to pick them down. dy dx is 0, which means that x minus y equals 0. If I were to solve that for y, we'd get y equals x. So that means that for any points where y is equal to x, the slope should be 0. Well, that means that anywhere along this line, the line y equals x, the slope should be 0. So I'm going to draw at every point that's on that line a slope of 0. And then we'll do the same thing with some other points. Let's let dy dx equal 1. That would tell us that x minus y is equal to 1, because that's what dy dx is. Or that y is equal to x minus 1. And so now we just need to look at the line y equals x minus 1, which would be this line right here. And everywhere along that line, we'll draw a slope of 1, because that's what we let dy dx equal. And then we'll try 2. And we should, with any luck, see the pattern that's going on here. We're going to end up with y equals x minus 2 this time. And that'd be this line right here. And so along that line, all our slopes are going to be a little steeper than 1. They're going to be 2. And we could test it out, but I think we could probably take a pretty educated guess that if I move down to the line y equals x minus 3, we're going to have slopes of 3. So we need to get a little steeper. And the next one's going to be 4. And this next one would be 5. And this last point here is going to be 6. And we'll test just to make sure with -1. But it seems like that should move up in the other direction. So if x minus y equals -1, that would tell us that y is x plus 1, which is that line. So everywhere along that line, we want slopes of -1. And we could test the next one again just to confirm it's going to continue the pattern, but it is. If we choose -2, we'll now have x minus y equals -2, or y equals x plus 2. So this one will be a slope of -2. And the next one will be a slope of -3, and -4, -5, -6. And we can see our nice little slope field. And a lot of times on the AP test, the score breakdown for sketching the slope field is that you'll get 1 point for all the slopes that are supposed to be 0, and then a second point for all the other slopes. So we get 1 point normally for these ones, the ones that were 0 right there, and then we get 1 point for everything else. And now we've got a couple interesting things going on here. The first is, let's say we chose the point about -1, 1. So we see that here we need to be at a slope of -2, right where I put the point. But once I come somewhere in, well, it's very well done, but somewhere along this line, it needs to already be at -1. And then by the time I get to this point, it needs to be 0. So if I try to sketch that, kind of going to just curve down to be 0, about like that. And as I go to the other direction, it's going to get real steep real quick. And on the other side here, something a little different happens. So I start at 0, and I have to get over a full unit to be up to 1 there. But as I'm moving up, these slopes as I go up and to the right are getting bigger more slowly. In fact, they don't get big enough quickly enough for us to actually ever reach that that line of y equals x minus 1. And so what we actually end up with here is an oblique or a slant asymptote. Right? We have a slant asymptote right there at the line y equals x minus 1. We're going to talk a little more about that in just a second. If I picked a point that was below that slant asymptote, like let's say I chose this point, right, we'd be going down, getting real steep, and going up and getting less steep, but never so unsteep that we actually made it to that line. Still be approaching that asymptote. And note that I've drawn both of these solutions from one edge to another edge of the slope. Now, one last little thing to mention here about this is, and let's see here, let's pick another color. If I asked you to sketch the solution that went through this point that happens to be on the line y equals x minus 1, well, I'd be at positive 1 of a slope. But everywhere along that line, it has a positive 1 slope. So I just continue all the way along that line, never deviated off of that line forever. Right? And so if we have a asymptote, but we ask for the solution on that asymptote, not actually an asymptote, the solution is just the line. And the thing to look out for to decide if there's an asymptote is if all of these slopes along a certain line have the same slope as the line, which sounds a little confusing. But the equation of this line in pink that I've drawn, or purple, is y equals x minus 1. It's this line right here. This line has a slope of 1. And our differential equation, dy dx, equaled 1, which meant the slopes of y equals f of x were equal to 1 all along that line. And so when those two things match up, this slope is 1 and the solution to the differential, not the solution, but the actual differential equation equals 1 at all those points, then that's what yields an asymptote. So we can see that with these other ones, like here, the slope is 1, but over here, we're plugging in slopes of 2. So that's not going to be an asymptote. But if it just so happens that this line was y equals 2x minus 2, then its slope would be 2, and our dy dx would be 2, and that would create a slant asymptote there. So I've kind of got this written out here on the next page. That if the slopes on the slope field along any particular line have the same slope as that particular line, it's going to create an asymptote for any solution curve to that differential equation that is not on the line, right? So that's what we're talking about here. The blue one wasn't on the line, so it's an asymptote. The green one wasn't on the line, so that pink is an asymptote. But if we're asked to find the solution on the line, the solution is the line. It's just the pink. So we're going to do one more slope field of one more type, and this is involving both x and y again, except this time they're not being combined together using addition or subtraction. It's a multiplication division type thing, right? So we've got a function of x times a function of y, or divided by a function. And so our technique is going to be similar to start. We're going to say, well, what would make dy dx equal 0? And well, the thing that would make dy dx equal 0 is if the numerator of that fraction was 0. So if x is 0, but y is not 0. And we'll note that at the point 0, 0, I haven't actually put a dot, because what does that do to our differential equation? It makes it indeterminate. And we can't have an indeterminate slope on our slope field. So first off, we'll just do the dy dx is 0 if x is 0, which would be everywhere along the y-axis except at the origin. And then we'll also think about what makes dy dx undefined. That would be if y is 0, and an undefined slope is just a vertical line. we'll just draw a bunch of vertical lines there. And that's the beginning of our slope field. And the technique for all the rest of this is going to be start in the first quadrant and kind of just pick a point. Let's pick the easiest one. Let's pick the point 1, 1. 1, 1 would give us 1/2. So at 1, 1, we're going to draw a slope of 1/2. And then we think about what happens if I move up, if I increase the y value, but keep the x value the same. If I go up to 1, 2, that's going to yield a 4. And if I go up to 1, 3, a 6. So those are going to get less steep as I go up. And the same thing is going to happen in that entire quadrant for each of them. So like if I start at 2, 1, 2, 1 is going to yield a slope of 1, like x in for 2, or 2 in for x and 1 in for y. So we'll start at 1, but as we go up, it's going to get less steep and less steep. And the same thing will happen out at 3, 1. We'll start at 3/2, so a little steeper than the one I made for 1, and then less steep and less steep. And that's really all the arithmetic we're going to have to do for this one, because if we think about, let's say, the second quadrant, in the second quadrant, the x values become negative, but the y values stay positive. And so all that's going to do is it's going to change the signs of everything that we've done in the first quadrant. In other words, it's effectively just going to reflect the slopes in the first quadrant across the y-axis into the second quadrant. So this one will be -1/2, and it'll get less steep as it goes up, and then -1 and less steep as it goes up, and then -3/2 and less steep as it goes up. And then if we think about the fourth quadrant, well, in the fourth quadrant, it's just going to reflect down below the x-axis from the first quadrant, because now we're going to keep positive x values, but change the y values to become negative. So we'll end up with -1/2, and it's going to get less steep, less steep. -1, less steep, less steep. -3/2, less steep, less steep. And either way we look at it, in the third quadrant, it could be a reflection of the fourth or a reflection of the second quadrant, right? Because either one is just flipping one extra sign. We're going to start at a +1/2 and get less steep, and then a +1 and get less steep, and then a 3/2 and get less steep. And here's our slope field. And so we could be asked to sketch through any of these points. Let's just say we were asked to sketch through the point 0, 1. We'd try to be flat, but then slowly we'd be curving up. We could do the same thing down below. We might be asked to start here at 0, -2. We just kind of slowly curve out. And it's kind of hard to tell, but if you were to find a slope in here, it looks like that slope would be 1/2. Along the line that has a slope of 1/2 in here, all the lines are going to kind of come out to give us an asymptote again. And so there's some values out here that we're not going to cross on the edge. And that means that we also have some other stuff going on here. So if I asked you, actually, let's use a different color for that. If I asked you to, let's say, find the solution to this point, it'd kind of curve out and up to here. But what I'm not going to do is curve it back around, because anytime we look at a solution to a differential equation, the solution curve is always going to have to be a function. And if I curve that, I don't pass the vertical line test. So we're just going to stop it right there where it becomes vertical. And so just remember to stretch to the ends of your slope field unless you have to stop to make it a function like we did with the green one. Make sure that it goes to the indicated point. You don't need to put arrows at the end. Make sure your solution curve is a function. And that's about all there is to slope fields. Just remember that they are a visual representation of what their solution looks like, right? The solution to that differential equation. And so this particular differential equation that we're looking at here, dy dx equals x over 2y, which I think I said earlier is a function of x, times a function of y, 1/2y. It's a function of x times a function of y. And anytime you have a differential equation that's a function of x times a function of y, that's called a separable differential equation. And so next time, we're going to take a look at how to solve separable differential equations, just like that. That's going to be it on slope fields and it for today.